Hey guys, so my name is Camilo. I am currently CTO of this for Thesys Technologies. In Thesys, we try to make markets better by using technology. That's what we do. I'm a software engineer, but I dabble a lot in product by managing my team and helping them to make great products. What I want to talk about today is what is software development from a non-technical standpoint, specifically in the sense of how can you help a team accomplish great things. My information if you need it. So the first question is why? Why do you need to have some chops on the technical side if you're a product manager? And the reason is simple. Like the first is you are interviewing for a position, and then you get the typical questions: what is your favorite product? How can you improve a product? What features would you add? How would you design an alarm clock for deaf people? Those are typical questions that you're going to be asked in your product interview. But then comes the question. Somebody's going to ask you, what happens when you write www.google.com in your browser? At this point, most people that I have interviewed personally, some people freaks out because they don't have any idea. They weren't expecting these questions. And when I'm interviewing a product manager as a technical lead, I don't expect the product manager to know the answer to this question. That's too much to ask. I think nobody in the world knows the answer to this question. There's too many details involved. But what I want to gauge is how much understanding of how the sausage is made. How much do you understand of the nuts and bolts of what it takes to make a website like Google run, or a small website, what happens in between, what things you can use in between to make the product better. There's a lot of stuff that you can answer to this question. So I will never expect a person to answer this completely, but the answer to this question will give me an understanding of how much has this person worked with a technology group before. There are many possible technical questions. Questions like, what is an API? What is a server? How can you track a user? What is a DLC? What are cookies? All those questions are in the same realm. Try to understand how much do you understand of how the software is developed. Getting the interview, you pass your interview, you get your position, but most importantly, while the job, you're going to have more things to do with the technical background. First, your job as a product manager is to make your team ship great products. And in order to do that, you're going to have to be an effective communicator. And that comes two ways. One way is being able to communicate with a technical team, and many times this is very hard. Technical teams are very jealous. They don't like people getting into their business and telling them what to do. But in many other cases, you're going to need to interface with business people, with clients, with users on behalf of the technical team. So being an effective communicator requires having a common understanding and language. And that's where technical knowledge comes helpful. Being able to understand technical trade-offs of different decisions, this is a big part of being a product manager. Understanding trends, knowing what makes sense, what doesn't make sense, what can be done and what cannot be done. All those things require some technical understanding. It doesn't require you to go coding, but requires you to understand how things are made. And the last one is very important, estimate implementation complexity. In order to decide what a feature is or how to break it down in a reasonable manner, you need to understand what it takes to get the feature out. So this is my agenda for today. I'm going to start by giving you a historical overview, and this is more of an annotated glossary of terms that have been developed over the past 50 years, with a strong focus on what matters for today. This is my personal perspective. It could be wrong, but it's the way I looked at the development of computing in general for the past 50 years. And then I'm going to talk later on what is modern software development, how does it happen nowadays. So let's start with a historical background. Back in the days, people will have these things, punch cards, and making code will have to do with making holes in these punch cards, pushing them through a machine and getting results back. There were no screens, keyboards, or anything like that. This is actually kind of the same that this is called assembly language. It's just a matter it's a way to write directly to the computer what to do. But this is very hard to do correctly. There are a lot of loopholes. And people, over the years, started working on how to make that better. So that was the 70s. The 70s were all about trial and error. In the 70s, some operating systems started coming up. One of the most important ones was Unix. There's ARPANET, that is the basis for the internet. Some languages to start going back from this to something that a human can understand, modified. And then these two are the most important ones that I want to point out. First one is in the 1970s, they came out with a language called C. It's a low-level programming language that allows you to do a lot of that you can do nowadays. And that allows you with Fortran form the basis for what we know as current software development. It started introducing concepts like functions, variables, types that were not clear before. And in 75, the transmission control protocol was defined, which is this is the backbone for the internet. This is the way computers communicate. Is the pathway that computers use to communicate with each other. Then in the 80s, if the 70s were all about the trial and error, the 80s, won. That's what was happening in the 80s. I don't know if this is going to work. Yeah. So the 80s were about trying to get those basics, like those basic concepts, and abstracted in ways that you can compose on top. So it was all about abstracting engineering models of how to interact with computers, how to program those computers, and how to interact with data. So in 83, you got the Osi model, which is a model that is still is used to understand how the pieces fit. But I'm going to focus mostly on these two, on the custom protocols and the way computing works at the time. Custom protocols were based on the TCP that I mentioned before. It's basically how to use that line between the two computers to transmit information. And there's a number of protocols that came up. FTP, SMTP, POP, IMAP, and IRC. And I mentioned these 5 because those 5 are still used to this day. Things like FTP are still used or are the basis for the way to move files. SMTP, POP, and IMAP are the way to send emails, so this is the basis for emails. And IRC is like 30 years ago. Also, the way you interact with a computer is very important. At that time, you used to have these huge monoliths running in mainframes, and then the computer will be there, and you have this thin shell that you communicate from, and just log into a computer, which is not unlike what we do nowadays with cell phones, if you think about it. At that time, we were able to come up with a standardized model for computing, and this is actually super key. Before, like in the 70s and 60s, people was trying to make computers. They were trying to decide what a computer even is. In the 80s, we came out with a construct that we can call a computer. And this computer is seen as a piece that is CPU, a piece that is memory, some bus that communicates, some I/O devices or peripherals with these two pieces. And that's mostly true as of now. In the couple last years, this has changed a bit. You have kind of taken this and put it like closer to the CPU, but the model still holds. Those are the pieces that electronically make a computer. But it's not only about the electronics, it's also about the way you think about the software and hardware. And you have these layers. So first you have the hardware layer. On top of the hardware layer, you have a program that is called the operating system that interfaces that hardware with applications. So most of the people that is programming at this level as communicating with an operating system, and then the user interacts with the application. So you have this layered approach to computing. In the 90s, we got the dot-com bubble. The dot-com bubble is a result of these things I'm going to be talking about. There is a bunch of things that happened in the 90s, but I'm going to focus on these two. In 1991, the Hypertext transfer protocol was invented. That's the way that currently everybody knows HTTP : // This was decided in 91. And then in 90s, like middle 90s, people started coming up with databases, open source databases, that allow people to create this 3-layer architecture that we call currently LAMP, or it was called LAMP, which is a Linux machine, some kind of database, some web server, and some way to make that web server serve pages. This is the reason why we had the 90s .com bubble. Any web application at the time looked like this. You have a single database, all your clients, and an application server, and it was just a monolith. One thing is all here that talks here, takes the data, transforms it in some way, and shows it in a web page. And that was like that for many, many years for 99% of the applications. Also in the 90s, we started having some interactions with the internet. Things like Mosaic that they became Escape and then became Mozilla are the basis for current browsers. HTML was in 1993. Then we have JavaScript in 96, and PHP, XML, and JVM came out in the middle of the 90s. But at the end of the 90s, in the 99, this company was founded, VMware. And VMware is very important for the 2000s. VMware allowed us to do something that has not been done before. I mentioned that a computer can be seen as these 4 layers: hardware, operating system, application, and user. But what if you take an application and write an application that is fake hardware, and over that fake hardware you copy an operating system and the application and user? And this seems like redundant, and why would you do that? This is what is called a virtual machine, and this is a machine. And the big reason why this is very important is because instead of having one single computer that is too large or too small, allow you to modify how much of a computer you assign to an application. And this eventually became what the cloud is, and the current models of deployment that we use today. So, the 2000s. In 2000s, again, so we have bye. 2000s were also the decade where a lot of these dot-com bubbles collapsed. People needed to do a lot of more complex stuff, faster stuff, and try to get more use out of the machines. So people started investing a lot of money on how to do proper development. And that's where things like project management, product management, and the Agile Manifesto came out. I'm going to point out 2 things: JSON, which became the default, the standard for communication between machines, and the Agile Manifesto here. JSON, if somebody is not familiar with JSON, is just this. It's just a consistent way to describe, these are called documents, which is basically a key value description. So you have any key and some description. Any questions so far? This is very useful because back in the day we have all these protocols I was talking about. Nowadays, instead of having many protocols, these different protocols, we all use HTTP and send JSON over that. Exactly. This is the basis for API. So API just becomes, what do I need to put here to get something back? That's kind of the result. Also, this set of really smart people that have been doing this for a while got together a scheme and decided to write these 6 lines. These 6 lines are called the Agile Manifesto, and I don't know if everybody here is familiar with it, but I'm going to read it because it's very profound. Individual and interactions over processes and tools. Working software over comprehensive documentation. Customer collaboration over contract negotiation. Responding to change over following a plan. That is, while there is a value on the items on the right, we value the items of the left more. This is key. Most people, when I talk to people, they're confused about what Agile means, and they say, Agile is Scrum, or Agile is Kanban, or Agile is Lean. All those things are Agile, but none of those things is Agile. This is what Agile means, and this can be interpreted in a number of different ways, and has been done before. There's XP programming, there's a number of other ways of doing Agile, but this is the core concept that you are going to have to deal when you're doing your product management role, is trying to keep these things in mind. Doesn't matter how do you implement it, and every company implements it slightly different anyway. After that, we also have a bunch of developments in computing. We have Git in 2005, which is a modern version control system for source code. 2006 was very, very productive for cloud computing. We came out with EC2 Elastic Cloud Computing from AWS, called General Availability. AWS Simple Storage, which is S3, general availability. Also, Hadoop 0.1.0 was released, which is a copy of a system provided by Google. And a lot of other things came out, like consumer electronics that are powerful enough to run applications like Android and iOS, and SSDs, which is less interesting, but it has to do a lot with computer. This is less important, but I'm going to go over that anyway. And it just shows you how much the processing power has advanced, and the capacity has outrun performance, which is even worse. So that comes from the fact that back in the day, the only things that you wanted to have in a database were transactions. So how many things I sold, how many things I got. But as the computing has evolved, you put more and more things in the database. So you need bigger and bigger disks. And this has this growth from the way capacity has grown allows you to do that. Nowadays, you have every single thing producing tons of data being pushed to the cloud, versus back in the day, you only cared about like how many things I solved. So it's a completely different paradigm of what is important. In 1991, 40 megabytes took 37 seconds to read one plate, which is 26. So it will take 37 seconds to read the whole content of a hard disk drive. But in 2006, it will take 52 minutes to read 200 gigabytes. So even though the speed and processing power has grown, the facility to take that data from the disk and push it through the computer is still very slow. That was a side note. In 2008, GitHub was founded, and GitHub, some people is confused between Git and GitHub. GitHub is just an application that runs Git. But this application provided a widespread use of Git as version control, and also provided a lot of people and common paradigms for people to use doing software development, like merge requests, pull requests, branching models. All that stuff came about because a lot of people was using the same concept, so they came out with a language to explain things. In 2009, DevOps, the term was coined, and DevOps is nothing but agile infrastructure. It's the same that was. Okay, DevOps, I was saying agile infrastructure was coined, and that has to do with the way software is developed. Back in the day, you had systems administrators, software engineers. The software engineer writes a program and ships over the fence, you would say. DevOps tries to avoid that. DevOps tries to have those two teams together, working together, making the program run. So this is about ownership and transparency. At that time, most of the computers, I showed the three-tier software model. In the 2000s, you started seeing some kind of breaking up of those three tiers into layers or services. And that's what's called the service-oriented architecture protocol. The basic idea is the web application is just a client for a bunch of services that can be running in the back. You'll usually talk about a dozen services. Each one of those have their own databases or their database access, and that allows us to grow up from very small web applications to applications that could serve a lot of people at the same time. Think Amazon, think Google at the time. They have to use things like this in order to survive, because they wouldn't be able to survive just with web. They cannot just get a huge computer to process everything that they need. Now, in 2010, we went breaking down the monolith and trying to make smaller things, and we hit some walls. And in 2013, I pointed out here, we came out with a thing called Docker. I didn't come out, like smart people came out with a thing called Docker, and Docker is just a way to use the Linux system in order to encapsulate processes. And that is very similar to what I had said before with the virtual machines. It's just trying to get like single units of processing that can do things, but that allow a revolution in how we do so. That I wouldn't say there is a debate. It is very clear that Docker is better than VMware, or like in general, containers are better than virtual machines because that allow you to ship way more stuff into a single container. The problem comes from other sides, things like security, things like easiness, reproducibility. Those things are slightly different. So if your team has invested heavily on getting virtual machines, then having a container technology is going to take them a while. But at the end of the day, this for developers has been great because you can have exactly the same production system in your computer. It's very useful. Other things that are very useful are Angular and React. They came to make software development for the front end more modular, and this is very important. Back in the day, you will use things like jQuery, plain JavaScript, even Lodash and underscore, but it was very hand-wavy how you make applications. Angular came from Google, and React came from Facebook. They have to deal with the problem of having a lot of people doing software development on the same application. Everybody's developing, like if you have 10,000 developers in Facebook or 20,000 developers in Google, they have to be touching the same system. So you want this system to be modular in a way that if somebody's modifying something here, it's not going to break there. And that's what Angular and React are able to provide. Nowadays, React is mostly the most common used modern framework for front-end. And it comes from the fact that even though there's a lot of boilerplate, it allows you to think of one component at a time. There were also some developments in big data by bringing Spark to the mix, and Kubernetes allows to take Docker and just spread it in large clusters. So to the discussion of what is a container versus a virtual machine, I mentioned that a virtual machine was like a mini computer inside the computer. So initially you have a server, which is the machine, a host OS, which is the operating system, and then a layer of interface between that and another computer, but that computer will be virtual machine, which will have its own guest OS, its own libraries, and its own application. That was good and all, but then it comes with a tremendous cost. You have to have this hypervisor or this virtual machine manager and this guest OS running in the same machine. So imagine when somebody is telling you something in English and you have to translate it in your head to Spanish in my case, that comes with overhead. So this is, while really useful, is not performant. With Docker, with containers in general, or container engines, what you do is you just bypass this guest OS, and what you do is you take the application, in this case application A prime, and B, and you just put them right on the operating system of the host, but you encapsulate them with a wall. And that allows you to have exactly the environment that you require to just ship things over the fence. It's tremendously useful. Then in the teams, there was a bunch of things that happened, but mostly it's taking what was developed in the 2000s and exploited to the largest level. So things like big data became very important, and because of big data, you have machine learning. Things like NoSQL that was defined in the 2000s became commonly adopted. DevOps was commonly adopted. Agile was commonly adopted, and microservices, as a result of Docker and Kubernetes, became commonly adopted. And those things the trend has been going over this like past 10 years, and mostly in the last past five years, where you see that Dockers are common household names for any development company that you can think of. These last term microservices. So I show how SOAP was taking an application and breaking down in pieces that they were communicating between them, the SOAP. You have microservices, which is basically doing the same but at a smaller level, taking each one of those applications and breaking them down into even smaller applications. And those smaller applications will have their own databases and they will communicate to each other. So this is what we call currently microservices. And microservices, they can communicate directly or indirectly, directly by using HTTP or REST or JSON commands via RabbitMQ, or indirectly by just communicating via, like, for example, a central hub or things like that. So when you start breaking down these applications, it becomes, you get to a point that things are unruly. Like, for example, if in order to respond to a request in this service, you have to go here and back. It's gonna, if something breaks here, this guy is gonna break, and that becomes not a good idea. So this actually was pioneered by companies like Google and Amazon, mostly Amazon with their two pizza groups. But they found very quickly that there are issues with this approach. So this brings me to my second part of the talk. My second part of the talk is about how is modern software development done? Like how do we currently do software development? So I finished with this, like this big mess of lines in a bunch of machines. Each one of those things could be a virtual machine or a Docker container, and they're communicating with each other. This is just too complex, and then it's too fragile. And by fragile, I mean that if something here breaks, everything can break in the middle. So this is a more common architecture currently. We have something called an enterprise service bus, which currently the most common ones are Redis, so Celery could be used, RabbitMQ, ZeroMQ. Anytime you hear an MQ, means one of these. And those you can think of as the backbone that communicates different services. So instead of everything communicating with everything at the same time, like we have here, you just have everything communicates with a single thing, and it becomes like a hub of messages. And this becomes your golden source. Everything that is requested or any process in action has to come through here and has to be written here. So that makes it very easy by any service that's interested to just take an action. And an easy way to talk about this is think about Slack. When you have a group of Slack, you can send a message, and anybody that's interested can just register in a channel, right? It's exactly the same that happens with the service bus. So for example, if this service is interested in people logging in, you just register to that channel and just take that information in. And these guys can communicate asynchronously with databases or with different UIs. So this is how modern architectures work. This is very important for you guys because you're going to have, basically this is a map of how your infrastructure will work, which is indirectly a map of how your teams work. So you're going to have a team that is UI, a team that is service 1, a team that is service 2, and people that is mostly managing the infrastructure to run these teams. The other thing I want to point out is about version control, and this is key to modern software development. I'm going to talk about Git. There are many other ones, but Git is the most common one. This doesn't work. Yeah. Git is a version control system. It's just a way that you can have a file with all its history, right? That's all it is. Is everybody here familiar with Git, or who? Let me correct. Who here is not familiar with Git? Awesome. So everybody here is familiar with the concept clone, push, pull, commit, checkout, branch, master, and merge. Awesome. This is typically how software development works, right? Like you have master or developer, depending on your branching model. You take a branch for your feature, you make a pull request or a merge request, and just push it back to master, and you have this cycle. I wouldn't say it's better. There are things why perforce could be better, things why Git is better. One of the things that Git makes very easy is to, let's suppose that we're all developers. We all, in our own way, have a copy of the repo. So makes it very decentralized. So he can take my code and merge it to his branch without we interacting with a central server. Perfor has this concept of central server, which is good for some software development, but is not great for open source software development. So this Git allows you to just share code in between different branches very quickly. Internally, the way Perforce works, the performance of Perforce is very different from the performance of Git. Git is very efficient at handling branches because it just has a direct acyclic graph that just takes branches and just takes notes and communicate with each other. So there is a bunch of reasons why you will want Git over Perforce. Perforce has a really good integration with tools. Integrates with Visual Studio, whatnot. So there are pros and cons. I will say at the end of the day, what you're trying to do is the same. But the reason why I would choose Git nowadays is because it's so widely adopted that everybody knows how to use it, and there is a lot of good tooling around it. With Git and GitHub came out a bunch of different problems. Is how do you use Git to do software? And there is a bunch of answers to that actually. There is a bunch of different flows of how to do your development. People have develop branch, feature branches, release branches. There are things nowadays called like GitOps, which is actually having your operations and your infrastructure in Git. But at the end of the day, it's just a branching system that Git doesn't care what your branches are. It just takes from one and puts it to the other. And this is very important because this is not only for software development. You can do very interesting things by using Git. Since these branches are autonomous, you can make actions happen when branches are touched. And that's what continuous integration and continuous deployment means nowadays. So for example, this is the version control system that the developer is constantly pushing into that. But if you make it a trigger so that every time you push commit into the main repo, something gets triggered, and that trigger just asks some build database to generate a build, then you can have very cool stuff like automated testing, which is tremendously useful. When you make your codes and if your project is well tested, then you will be able to see or if your code changes, break something or not immediately. And that makes the speed of development much faster, much more higher speed. And it's not only about the continuous integration. So continuous integration deals with taking these these source code changes and testing it to make sure that they're well integrated with your code. This breaks the model that was used before and is still being used in many places, where people was shipping, was talking about big releases, and then you will have a team working 2 weeks in a feature, and another team working for 2 months, And every time they will try to merge it, something will break, and they'll have to spend another 2 months trying to figure out what breaks. If you keep your branches short-lived, meaning 1-2 days, try to keep your features small, or use things like feature flags, then this becomes very easy because you're constantly pushing to your master or develop branch, and then constantly things are getting merged. And you don't have these large merge conflicts that used to happen before. And the testing is very important because now you can confidently, like the developers became very aware of trying to automate the testing. Back in the day, you'll have people here like QAs and QEs, quality engineers or quality, analysts, that they'll have to sit down and reproduce every single piece and part. So you'll have a feature, you'll have like this long list of things that they'll have to check, and they'll go and click out. But if you can automate all that, you'll feel more comfortably. So currently in my systems, we do hundreds of pushes to master every single day, and we are confident that we're not breaking anything. And if we break something, we are going to use that information to create a new test that is going to catch it the next time. So this is extremely powerful. So this is the continuous integration part of it. Now, the continuous deployment is when you take this version control and these triggers to generate builds, then you can use it also to trigger deployment. And that's a part that most people doesn't do. It's extremely hard to do confidently because most people doesn't trust their test. But this is actual freedom. Like when you know that any change that you want to do, you just have to commit it, and eventually it's going to get pushed. You don't have to touch it. That's what is going to give you the most speed and allow you to be truly agile. So that's what continuous deployment means. It means that every time there's a change in one of your main branches, the release branches or deployment branch, this gets pushed automatically via some orchestration system to your application. And that's it. So that's my talk. I know it's a lot of stuff and very fast, but if you have any questions, just let me know. 100% automated testing, that's a hard question to answer because what is a test? And there are many kinds of tests. You can have integration tests, unit tests, functional tests, non-functional tests. So having being able to say I have 100% of every single one of those doesn't really make sense. There are things that doesn't make any sense to test, even like, for example, calling a library to set up a database. If you're going to have to mock it, you're going to be using a different code anyway. So I don't think people ever get to have 100% coverage on their unit test specifically, but you got to be comfortable when you're pushing. So in my case, that comfortable is 80 to 90% usually. That allows you to say, yeah, everything I push has been tested. And it also comes from a mixture of two schools, the Chicago School and the London School of Testing, which is test everything from the outside in, being able to just test the interactions and the big level features, but also test the individual units of work. So I don't think people ever get to 100, but you got to start to have something over 70, I would say.
How far can you talk? Can you elaborate on that?
That's really, 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 really important. So the fact that I took my code and I pushed it and it didn't break anything doesn't mean anything, right? It just means that I didn't break anything. But it doesn't mean that I was able to complete the feature request that was provided or that I did it in the best way, right? And that code review piece is one of the most important pieces for learning. If you're trying to mentor, for example, junior developers, that's where the learning happens. I personally get my team to be extremely critical, to the point to be annoyingly critical about code, because that's where everybody gets together and says, this could be done in a different way. So let's talk about what code review means. These guys here are called branches, or feature branches, and this is master. Master is the source of truth. We said this one should at any time be stable, which means should be deployable. At any time, I could take whatever it's in there and push it over the fence and be completely certain that nothing is going to break. But this is problematic because if we only have these ones, and things like Perforce will have this problem, is that if we only have this one, I cannot confidently make any change because that will break stuff. So how can I do my code changes that break stuff without breaking production? That's when you talk about branches. So in branches, you just have your branch, which is just a branch on your source code, where you're doing your code commits constantly. You're constantly testing and making sure that everything is working. And then you can take all these feature branches and either collapse them or pass them through a merge review, like a code review tool that will allow you to see all your changes in a single place. And then one or several of your colleagues will take your changes and say, hey, this could be done better, or this was really well done, this requires more testing, or this didn't complete the feature. And that's where you get your team to discuss. And initially people, it's very apprehensive to doing that because it gets personal, right? I went and spent 2 weeks and generated this amazing algorithm that will be able to do this very quickly, but the code is unreadable. So what does it matter if the code is very performant if nobody can read it? So that's, if somebody tells me that your code is not good, I will say, but my code is very fast. But in reality, it could be fast and readable. So what I emphasize with my developers is you should make sure that whatever code that you're reviewing is very readable. So that all happens in the merge step. Once everybody that's supposed to do the code review is happy with the reviews, they could include more commits, more tests. Then one developer, it could be the same developer, a different developer, is in charge of taking that and merging it to master. And so that's how code review happens.
A couple of questions that they might be related. When people talk about cloud and AWS, what does that mean in terms of what people are doing today versus what they should be doing in the future?
That's such a good question. Cloud is just a computer that is not yours. That's all it is. Why is cloud important? Is because back in the day, if you wanted to run your system and your system had 110,000 visitors in a month, even 1 million visitors in a month, and it's a blog, this computer will do it. My cell phone will be able to do it, right? But if your system requires some kind of serious computation in between or has a database, then you need not one computer but 2 computers. And let's suppose that you are growing tomorrow, so you will need 3 computers, and then it gets very annoying to say, oh, I need another computer, let's go find it, let's connect it, plug it, configure everything. So that's what clouds provide. Cloud provides you a very efficient way to scale up and down resources. So that means that instead of, and that comes to the virtual machines, they have in Amazon or they have in Google on Azure huge racks of these guys, and they're tremendously huge. They're computers with 500 cores and several terabytes of RAM, and they just take those and just break them down into pieces that are virtual machines, and they give you virtual machines. So for them, the virtual machine takes 1 minute or 5 minutes, depending on the cloud, and they'll be able to give you a computer exactly with the characteristics that you want. So if you want 10, you can spin them up. You don't need them anymore, you spin them down. So it provides you economies of scale. So Amazon and Google, they have so many computers, and they're competing with each other, so they allow you to get compute very cheaply, right? And that was the first version. That's what is called EC2 in Amazon, Elastic Cloud Computing. But then people start hitting our problems, like what if I have a huge computer or 1,000 computers, it doesn't help me if I still have problems with my database. Because database you should call it state. You have to take that database and copy it to every single one of the 10,000 computers, or split it, or do things with that database, and that becomes really hard. So Amazon and all the cloud providers have been working on ways to take a database and split it and make it perform in the same way. So the same way I can get 1 or 1,000 computers, I should be able to have a database that says 1 or 1 million clients. And that's why S3 initially was built, and DynamoDB. There's a lot of advances on that field, and there's big file system from Google. There's a number of things that happen that way. So initially, the cloud infrastructure was compute and storage, right? But then a lot of patterns became common, and patterns like this pattern, for example, become really common. So if everybody is using an enterprise service bus, why shouldn't we provide a large database and a large enterprise service bus? Or if you require some fronting server to load balance your UI to the services, why don't you provide that? So the cloud became, instead of having just infrastructure as a service, it became a platform as a service. And it started giving you all these tools that you can just combine and make your applications, right? So a lot of people that come from the older ages, like me, I'm old, I think of the cloud and I just think of, yeah, compute and storage. But that is not really giving you the most bang for your buck, right? If you're having to code your load balancing, your Nginx, your APIs, your gateways, all that stuff by hand, then you're going to be redoing a lot of stuff that's already been done a million times. AWS nowadays is providing a lot of infrastructure and services that allow you to do pieces and put them together. But you're still thinking on services. If you're thinking about this way, you're still thinking of a server that is running some program. And to answer your second part of your question, how it's being done currently, how should it be done? You shouldn't be thinking of service anymore. So like the new way, the way that has been pushed since Lambdas were pushed to production in 2013, I believe, is that why do you pay for a server if what you want is to run an application? Why don't you just run for you should be paying for the application itself. And that's why the serverless movement comes that requires these decentralized data stores, again, Dynamo, some kind of trigger API, and then just these tiny units of work that take a unit, process it, and push it somewhere else. So serverless is the best way because then you don't need to have all these complications of servers filling up. You don't need DevOps, you need sysadmins. It just life becomes easier. And the developer is very empowered about what or what not you get to do. So definitely, I'll push for serverless whenever I can. Traditionally, most people will stay away from serverless because they don't understand it or they don't trust it. And there are some drawbacks to obviously performance and startup times. Thank you. That's it.